This picture is from Athens. This is what they call Parthenon. There's a big history behind these ruins. They're considered to be, I think, I don't exactly know how old are these, but yeah. This picture, so we'll continue our discussion. Biosensors. We talked about biosensor last time. And biosensor has three major parts. There has to be a target or analyte that we are looking for. And this is something which can be of interest from any source. It can be a human source, animal source. We are looking for air. We are looking for water supply. It may be a chemical. It may be, and chemical means a molecule. It may be cells. It may be some biomarkers. So whatever is the case, we call it target molecule. We also call it analyte. And then we have to have a recognition element. You would see the different names that would be used for that. So recognition element can be called also a probe molecule. Probe molecule, like on a surface, what we put down. Sometimes we use receptors. So we would call them bioreceptors in that case. So there are many different entities that are used as recognition elements: enzymes, cells, nucleic acids. Then there are types of nucleic acids, aptamers, antibodies, a whole range of things that can be used as recognition elements. Now, the binding of those target molecules with the probe molecule, with the recognition molecule is going to result into the generation of a signal. And that signal can be light, can be heat, can be oxidation, can be change in pH, can be the change of mass because of the binding. And that happens when there is selective or specific binding that occurs. And that's something which would be then translated into a signal through a transducer. So this change has to be then transferred from one type of energy change or one type of interaction into something that can give us a signal to the outside world, to us. So that's the transducer part. And that's an element which would take this signal, which would take this energy, if you can call, and convert it into another type. In biosensors, it would change this biorecognition event into a measurable signal. And that signal can be, again, can be light, heat, pH, all the things. But now when it's transduced, it goes into a detector that can give out a number, which can change a scale, which can light up an LED, whatever the ways we would be looking for the binding event there. So more often we use optical or electrical signals to get a measure of the recognition. So when we talk measure, then we want to see how much of it is going on. So we'll dissect this today. We'll look at various parts of a biosensor and what makes a good biosensor. And it fits well here now. I see many of us have now read some literature built up on what we have studied so far, and now they are thinking about developing a kind of a research idea. So this is going to help there, that what may be essential parts in designing a good proposal, right? Biosensors are nothing new. These have been around for a long time. For as long as 1960 that we know biosensors have been developed. And over years, there's been new inventions that have came about which have enabled better biosensors. So first biosensor which could be used for a commercial application was in 1962, glucose, right? So we know glucose sensor, all of us are aware of glucose sensor. And we look at glucose sensors today a little bit closer to see to understand a biosensor and what goes into that. Now, those biosensors have come a long way. This figure shows it up to 2001, but now we have much, much more advancement from just simple uh, pricking into finger and getting blood out of it and looking at blood. We have newer ways where we don't have to get the blood out. But the blood test still stays the what you call gold standard. That still stays what gives you very accurate measurement on what's going on. So now talking of glucose sensor, it has a major impact on us as humans. Every year, millions of people are getting diagnosed with diabetes. And very interestingly, majority of those people are from low and middle income countries. So diet, exercise, so whatever the reasons they go into that. But the thing is that the number is increasing, and there are reasons like population aging, diet, obesity, lifestyle, and we are still using a lot of blood-based glucose sensing, while there are new things that have come out, new ways that can be done. But studying by glucose sensor helps us look at some parts that go into that. For example, it is a sensor that does amperometric enzyme detection. So it started with us learning immobilization of biomolecules and stabilization on a surface, right? Now, once we do that, we can miniaturize, functionalize that, and we are able to get the oxidation of glucose as a signal. So when glucose oxidizes, it turns into what we call glucose oxidase. And there is now this, the glucose oxidase is a catalyst that results into oxidation of glucose. And that gives us gluconic acid change in pH, which means there is more hydroxyl groups. Oxygen is getting depleted, and that results into a voltage change at the electrode. And that voltage change is now measured, and that tells us by calibration now we can know exactly how much glucose was there in the solution to start with. So GOD is the catalyst that results into oxidation of glucose, and that gives us a signal, electrical signal, change in voltage. This has helped us move things much faster for other kind of sensors also. But in a glucose sensor or many other sensors, we use enzymatic electrodes, where we have the enzyme which is coated on the surface, and once there is a binding that occurs, it results into an electrochemical change, and that gives us an electrical signal to the outside world. Now, enzymes are molecules, right? They're proteins, which gives us molecular recognition activity. So there are many types of enzymes that we know now. And this binding activity is what changes the electrochemical properties of that surface or the measurement system. Now, there are enzymes, a whole long range of enzymes. There are many antibodies that we put down on the surface. There are many receptors we put down on the surface. So what we call functionalized surfaces, which give us the recognition capability. So many of the biosensors which are commercially used, they use enzymes. There are enzymes which are called redox enzymes, so reduction and oxidation. So that's a process where we lose an electron or we gain an electron. So loss of an electron is called oxidation, gain of electron is called reduction, right? Redox, reduction, oxidation. So they are more frequently used because that oxidation, gaining or loss can be measured electrically. So this example is showing an enzyme layer, an immobilized enzyme layer, and then there are different parts of it. ultimately what we are doing is we are measuring change of that. We are measuring the redox reaction at the platinum electrode. So over 50, 60 years, it used to be many devices, big devices, gadgets, desktop. Now we have reached somewhere where within a second or so, we can get results. And for blood-based, all we need is 1 microliter of blood. So when we do this needle prick, we get a whole lot, much more than microliter, but all we need is 1 microliter. We know we use strips, we take the blood and put it inside the machine, gives a number. But now we have devices which are giving us things where we don't have to even inject anything. So we have patches like this example given on the low left side called freestyle liver, just placed on the arm, and it can be worn for many days, for 1 week, 2 weeks. And this patch measures the glucose level in the interstitial fluid between the cells right under the skin. And that data is something which you can record on the device. The measurements, they give good real-time numbers, but they're still not as accurate as a blood test. When you talk about accuracy, that's a property of a biosensor, which we'll discuss. How do we define accuracy? So people can continuously and wirelessly measure their glucose, but then they still need a reading device, and then they have to get tested after some period of time to get the blood testing done to make sure that it's calibrated, it's doing what it's supposed to do. So, and then there are sensors which can detect glucose through combination of many other things. Ultrasonic, they are using electromagnetic waves, they are using thermal waves, they are using a simple patch that can emit a signal and measure the signal, and that can give us a result. They're making this finger clip type of sensor also for glucose. So we have come a long way where we have non-invasive kind of things. We can wear them. There are implantable things which can be implanted and they can continuously measure. And we still want to, there's still room to improve what we call smart sensors, where we want to automate, where we measure and we pump the insulin also as needed. So this is also already there, but needs to be, there are issues where clogging of the system or the malfunction, we still need to do much more work on that. Let's see, I have some chat questions. All right, can you guys hear me okay? I don't have many videos on. Can you guys hear me? All right, very good. So, okay, so that's an example of glucose. Now, what are all different types of sensors out there? What kind of things we do? So we have seen electrodes, like where we use nanowires or carbon nanotubes. But now you have to think broader. There are not just wire type, there are thin films. There are light optical fibers, which are used to see the sensing mechanism. There are MEMS system, of course. There are devices where we flow through a sample and they can measure on an electrode, where you can measure maybe capacitance between two electrodes. Maybe you can measure the electrochemical kind of interaction. So many different ways how we can create devices. What drives the design of these devices is generally what kind of transduction we can do and what kind of application do we need from them, right? So we can classify them based on the transduction, the potential, current, electrical, light, temperature, mass, or we can also classify them based on the need, based on where we are using them. It may be just to be used in a lab environment, which is much more cleaner. We have people who are trained to use those sensors. It may be where we have to use it in a rugged environment. We have to deploy in the field. Now, again, people need to be trained, but the environment can be dirty, which means background. So we'll see for all these different sensors, what may be the issues or what may be challenges in those. It may be a sensor which what is called inline process monitoring. So in the industry, when we are making something or there are some chemical processes going on, we have sensors which are dipped in the solution or in the process parameters, and they're measuring the process parameters. They're maybe looking for pH, maybe looking for temperature, maybe looking for if there are any gases being created. They are what we call inline processes. In semiconductor device manufacturing, we use lots of metrological tools, so which are inline process monitors. It may be in vivo, which means that we are looking for blood or a solution inside the body. It may be not just liquid, we may be looking at heartbeat, for example, different features of the body, acoustics, solution, expansion, depression. There is like DNA microarrays, high throughput screening, where we are putting dots and seeing the reactions, or what do you call now nanomedicine, personalized medicine. There's different names of that, nanomedicine, personalized medicine. The idea is that each person, so the sensor should be tailored to every person, because every person has his or her own body makeup. And when I say body makeup, I'm not talking about physical, how we look like, but inside the chemicals that our bodies produce. A very interesting example is prostate specific antigen, PSA. So PSA is a molecule which is known to indicate prostate cancer for men. And men over 40 years of age, they say to get tested for PSA regularly. But then for PSA, it is known that for some people, high level of PSA does not mean they don't have prostate cancer. But some people with low PSA level do have prostate cancer. So that highlights the requirement or the idea of personalized medicine, that every person's profile, genetic profile, the molecular profile should be part of the design of the sensor and the therapy as well. So the drug that's given to a person also needs to be tailored to that person. So high throughput is the idea, high throughput screening, like the DNA microarray thing, where we push through a whole bunch of biological solution and we look for specific molecules. In the drug development also, it is done where they try with a whole different bunch of chemicals and they want to see how those chemicals would act on certain disease cells. So if there are some compounds that work effectively, they are identified as potential drugs. It's a long process, but the idea is high throughput screening comes in many shapes and many applications, but it's a kind of a biosensor. So now if you think about the different applications, so the challenges can be defined according to those applications as well, or the requirements can be defined according to those applications. For military, for biosecurity, or for field deployable, we need them to be user-friendly. We need them to be robust. We need them to have low false results, right? We need them to be able to operate in varying high temperatures and low temperatures as well. For implantable, we want them continuous, because once they are implanted in the body, you cannot keep opening the patient apart and trying to add more. So we cannot add reactants from outside. We want body to not have any foreign body reaction to it, right? So it should not create fibrosis. It should not reject it. And then if you implant, then we need to find a way, how do we get signal out? So there's lots of work that has been done on that. So for example, pacemaker, it's very straightforward. You put the receive, what do you call, readout to the, so pacemaker is generally placed here. You bring the readout here and can wirelessly get the data transferred. So all these different applications have their own challenges and their own requirements. But at a very fundamental level, every biosensor has certain basic design criteria or performance criteria or requirements. Let's look at those, because unless we know these features of a sensor, we cannot make a claim about its efficacy. We cannot make a claim of how good is that, right? So sensitivity, detection limit, selectivity, dynamic range, stability, response time, spatial resolution in space, how often can we take the data, accuracy and precision or repeatability. These are very important aspects of a sensor. And how do we make sense of that is each one of those are clearly identified and understood, many times independent of the other feature, but sometimes they are interrelated. And we'll see some examples or how you can make sense of this. So sensitivity is generally it's an absolute quantity. We need to know what is the sensitivity, because this would tell us what is the smallest absolute amount of a change in the analyte that can be detected, right? So analyte, again, target molecule, what would be the response? So this response, or this is showing on y-axis, can be electrical, can be optical, can be change in mass, can be whatever transduction we are using. But it is the slope of that curve that we get from the data point. So here it is showing a continuous line. Of course, continuous line is just a model. When we are talking about sensor, we always have discrete data points. So the discrete data points is then we put a model line onto that. We put a fitting line to that. Now, many biosensors have a linear transfer function, which means that the sensitivity is defined as a ratio, right? A slope. Now, the output signal or the response has to directly match with the property that's being measured, right? Analyte concentration in there. The higher the slope, more sensitive the sensors would be considered, right? Now, if we talk about a sensor that has sensitivity change, if the temperature changes, we need to know at that given temperature, what should be the sensitivity. So that should come as in data sheet with the sensor. Or we in the lab, if we are working on sensor, we need to know what are the conditions for that slope where the sensitivity holds, right? So for example, some sensors, and we'll talk about nano sensors, if somebody walks by and it detects the vibration, your curve will have vibration in it, right? So there'll be a kind of a statistical error, and there's a way, how do we do that? But that will not be considered part of sensitivity. That will be another factor that goes into that, right? So we call that detection limit. So how much variation or how much signal variation can it withstand or can be reliably considered as part of the sensitivity? Now, many times we confuse sensitivity with accuracy. So accuracy is a different thing. So accuracy is the idea of the true results, that what is the ratio of getting true results, right? True false positive or false negatives. So it's a different thing than sensitivity. So now the numbers that we represent for sensitivity, they are generally the probability of a diagnostic test, right? So we get the curves for given conditions, and those curves may have some variation, and that's okay, but that will be considered as the statistical variation or the probability of a diagnostic test to have this sensitivity, whatever the number we have. Now, another important thing that goes with sensitivity is the limit of detection. How small of an analyte can we measure? Here, I'm showing a straight line starting from 5, right? So which means below 5, my response maybe is not valid because the limit of detection of my sensor falls apart. And there is another metrics how we understand that, right? But for a sensor, when we talk about sensitivity, we need to know the limit of detection as well, which is that how far on the lower side or the higher side can it detect reliably. That below that level or higher, more than that level, it may be saturation that takes over, that the sensor surface, the recognition element gets all saturated. So whatever data you're getting is not relevant or related to the actual amount of analyte that was there. Or when we go down, then if our data is being the statistical variation is much more pronounced than the actual value of the signal that we are measuring, right? So, for example, in case of prostate specific antigen, and the example I was giving before, so 4 nanogram per milliliter is associated with the prostate cancer probability, where then the doctors would suggest to get a biopsy result, right? So lower than that, much higher than that, we would not be able to, much lower than that, we would not be able to use this number as a viable sensor or sensitivity limit. All right, so another thing about sensitivity is signal resolution. So if I'm detecting 2 samples which have concentration C1 and C2, what is the smallest difference in concentration that it can resolve? Now, you see 2 curves, response to C1 and response to C2 on the left side. You see there the trailing edge of the first response is overlapping with the starting edge of the second of the response to C2, which means that in that area, we wouldn't know the response is because of C1 or response is because of C2. So we have to improve the sensitivity of that in a sense that the response of C2 has to be clearly separate from the response of C1. So the distribution of the signal would tell us what is the standard deviation, what is the mean and standard deviation. So if the signal from another analyte falls in that, which means they're overlapping, and it is not a good, it's not sensitive, have good sensitivity if the signals overlap. But if you have the red one and the left one, that would mean it's more sensitive for both of those things, right? So a little bit about sensitivity. Now, many times we have background, which means the signal at 0 analyte, you don't have anything that it's supposed to detect and it still gives a response. So the background can come from instrumentation itself. It can come from other molecules in the solution that may be interfering with the recognition element. Or there may be a baseline activity from the ions in the solution, right? So any biological sample would have lots of ions floating around. And this is where the people walking around in a sensitive measurement, that the vibration will come into that. So that means that we have to know that what is the bottom way of the limit of detection, where the background becomes much more pronounced, that we cannot look at the signal itself. All right, detection limit or limit of detection. So these are 2 different things. Limit of detection is that how far can we go? Detection limit is something that where we have the 3 sigma. We can measure when you get a signal, we can find the 3 sigma. There is a statistical way of we find 2 to 3 deviations of that signal. So response has to be more than the background response plus 2 or 3 standard deviation. So if I'm measuring a signal, now this will define the lower end of the limit of detection, right? So lower end is restricted by the detection limit, and the upper side is restricted by the concentration saturation. So the biosensor's resolution is the smallest change in the concentration of the analyte. But if the smallest change is smaller than the background or the limit of 3 sigma, which means we cannot reliably make a claim that the signal is coming from the analyte itself. It can be the noise, or what you call standard deviation in the signal. A good resolution is required where we not only do the analyte detection reliably, but also measure its concentration over a wide working range. So not just knowing that analyte is there, but knowing the change, the delta going from one concentration to other concentration. So the slope and the detection of the selectivity of the analyte or the target, they both make up this thing, which is the linearity would fall into the statistical distribution at the lower end. All right, so detection limit. So it's the same thing. All right. So then what you have to ask is if you go from some response to the higher response, so the analyte concentration is increasing, you're getting response. So does the variability stay the same? So 3 sigma has to stay the same. If you get higher variation, which would mean then it is not the background which is causing that, or it is not the signal, or it is not the noise. There is something else that would be causing that change in the variance. So change in the variance has to stay around the mean signal that we are measuring. All right, so dynamic range. Another important part of a sensor is that when we are changing the concentration, it has to have a predictable dependence on the concentration. So, and if it doesn't, that would be where we would put the limit of detection, LOD, minimum and maximum. Even if we are getting signal, but if it is not dynamically changing with the analyte concentration, we have to put limits on those 2 sides about the sensor sensitivity. Selectivity. Now this has to do with the recognition element, or the enzymes, or antibody, or aptamer, whatever we use to detect our target. So this is probably the most important feature of a biosensor, because this receptor recognition element has to be specific to the analyte. If it is not, we'll be getting false results, which again would not give us the results about what we are looking for. Now, a sample may contain many other things in whatever solution we've got. And there are specific things what we can do. The background or the ions that are floating around or other molecules, they may interact, or they may result into what you call biofouling, where they may stick to a surface and clog that instead of the actual analyte that we are looking to bind there. So, and many times we know their reactions in a test tube, right? So as a chemist, the reactions are already characterized. But when we put them on a surface of a sensor, there are bio-nano interface issues that come into that. And there's a local radius of gyration, how much that molecule can float around. There is a local restriction of the surface. It's called static friction from the surface itself. There may be the surface itself has charge in it, which will result into pushing these similar charged ions away from the surface and pulling the opposite charge to the close to the surface. And what we know from the folding of proteins, that folding requires certain charge or certain location of charges for them to be functionalized, to be able to do their recognition. So we use antibodies, aptamers, DNA molecules many times on the surface of a transducer. So this is something where we need to know that the specific or selective activity is still good enough on the surface. So there is then a percentage of interference that is measured to talk about how good is that that sensor in given situation. Now, how do we improve selectivity? We may need to get a better recognition element. We may have to then change the whole chemistry of putting molecules on the surface. Some students are looking at graphene oxide, right? So now graphene, you have graphene, so you have carbon oxide bond. How would you functionalize a molecule that will bring there? If you functionalize the molecule that in solution may have the recognition capability, now you're bringing to the surface, now you're binding it. Would it maintain its binding affinity with that target molecule that we are looking at? So sometimes we need to modify the recognition element. We need to interface, change the interface. So sometimes, and it has happened, we'll look at some examples. You may have to put a linker molecule on the surface. So which would mean you'll create a SAM or self-assembled monolayer of a linker molecule, and then you'll have to put your recognition element on top. And the reason is to reduce or reduce the effect of the surface, which may be charges, stiction, or roughness of the surface maybe. So there are many things that would go into for us to modify the interface. We may have to do some pre-processing of the analyte. So maybe we need to spin it and get rid of some other molecules that are there. So which means pre-separation. So before we introduce them, we may have to do some, for example, in blood samples, many times we have to get rid of RBCs, red blood cells. So there's some solution that we mix that breaks apart RBCs. So you do that and then you use that for whatever detection we are doing. We may have to develop a new recognition element. So many folks work on exactly that. They are looking for new recognition elements, or there's an area called aptamer detection. So they start with a bunch of random molecules and they see their reactivity with one target entity, and then they identify which one binds the best. We may, in that recognition element, we may completely change. Instead of using maybe an antibody, we may use a nucleic acid. So it depends on the application. Or we may have to change the signal identification method. So maybe if you're doing charge transfer, we may have to do a capacitive. If you're doing capacitive, it's not working, maybe we need to put a piezo material to look at the mass change. So that also sometimes comes in where we might have to change the signal identification method. And this is the question I asked a team, and they said, okay, we want to use that kind of nanomaterial to do something which has already been done. So my question is, by changing this identification or this binding, what is the benefit we are getting? So for example, quantum dots, it says more than one response to each analyte. So quantum dots gives us that capability, same material, but different wavelengths. So you can take quantum dots of different sizes and separately functionalize them with different recognition elements and then mix them and inject. So now we know that different wavelength has been functionalized with different recognition element. If you remember that picture of that mouse which had 3 colors coming out, they are quantum dots. Each size quantum dots was functionalized with different recognition element. Hence, they all went and got bound to different parts of the physiology of that animal. Can we classify classical physics experimental apparatus as biosensor? For example, X-ray machines are also used for detection of bone fractures. Now, yes, X-ray machine is giving you a physiological picture of what's happening inside. But when we say biosensor, generally we talk about, look at the first slide. This is where we talk about looking at biomarkers, the molecules or body, what's happening inside kind of things. And we take them out and we try to get a picture of what's happening inside, looking at the quantities or changes in the concentration of those biomolecules. But then we have MRI, we have what you call equipment that uses non-invasively looks what's happening inside, right? They're kind of biosensor, but when we talk about biosensor, generally we think more about molecular detection, molecular level detection, or organ level detection of disease indicators, right? So stability is another important aspect. So many times we send a paper and they say, okay, oh, nice work, but how long can they stay active? How long can this work? How long does it function? So if you're making this new interface, maybe you have come up with a new molecule that you want to put on the surface to detect something. Is it good enough? Can it stay active for a long period of time? Because many times the response degrades over time. And it's most of the time it's because of the degradation of biological molecules that we are using as recognition elements. And there are many reasons why that would happen. For nucleic acid, for RNA, there is a RNase activity. So there is a enzyme which breaks apart RNA. So we don't like to use RNA molecules unless we modify them, and there are modifications that makes their structure stabler. And then we have used RNA as recognition element. But that is something where if you functionalize the surface and you show that I can detect something, sometimes there is another question of regeneration, that can you now get rid of what you detected and use that sensor one more time, 10 more times, 20 more times, because the idea is that if you make a chip, can you use it multiple times to do one detection? So that's another thing that comes into that. But generally, stability is that is the degree of susceptibility of the changes around the biosensing platform. That this changes in maybe temperature, changes in pH, changes in other enzymatic activity, can that withstand all those things happening in that? And over time, these activities can cause a drift in the output signal, which means, remember that the curve can change. So this is just showing response to one concentration over time, right? But if we go back, what was that sensitivity, those straight lines? So over time, that can change. Now, how would I know that what is the response of this biosensor if over time it has degraded, right? So this would be something that would go into the question of stability. So, and this can cause in the error of the measurement, and we would be thinking we are getting some concentration while it is actually measuring some totally different concentration. So it would affect the precision and accuracy of the biosensor, right? So this is another crucial factor which helps us understand if I'm selling a biosensor and I'm selling for the glucose meter and I'm selling my strip, say I'm selling a sensor for one disease and I'm selling some strips that have to go with that, how long can they stay in storage before somebody buys them and uses them? So many times this is something which becomes an important factor for a biosensor. Now, electronics can be also adjusted sometimes. So if you know that a biosensor is going to change its feature over time, and we know how long and what to expect, then we can, in electronics, we can input new parameters and say, hey, this sensor is, I don't know, maybe 20 days old now or 20 months old. So the electronics can sometimes cater for that change and use a new profile, the profile that they would have tested in a lab environment before they send out to sell the sensor. So that's something which can alleviate this problem to some extent. But very important aspect to know that how stable it is for how long. Response type. So we do a measurement and we do it in a given situation, again, some temperature. How long does it stay? The response, how long would it keep on giving the response? So, or how quickly would it give that response? So say if I am doing a reaction, or if I'm looking in the field for some toxin, so would it be able to detect it right away, or does it require some binding and then some reaction and some enzymatic activity before it gives a response? So that's what we call as response time. So in other words, we have to know how long would it take for it to get a measurement or actual measurement of the system. Now, if you remember silicon nanowires, there was a presentation on that. So they always show in the plot that this is where the analyte has been added, and this is where you start getting the signal. So if you remember those graphs, it's a big metric of what is the response time of that system. Accuracy. So a different thing from sensitivity. So the idea is that, can we reproduce that? Can we reproduce the biosensor to generate identical response to duplicate that? Many times it has happened and still happens. People publish a paper, they say, okay, we did this, something fantastic. Other people cannot reproduce those results. Puts a bad question mark on the validity of those people who would have published the original paper, right? So reproducibility is again characterized by the precision and accuracy of the transducer and electronics as well in a biosensor. For glucose sensor, the gold standard is blood test, right? So whatever new devices or patches or other things we do, we always want to go back and they show that how does it compare to the gold standard, and gold standard being the blood measurement, right? So now we say there's precision and accuracy that goes with that. The precision is the idea that how good can it reproduce its signal. So you do some measurement, if you repeat it, can it precisely reproduce the same thing? So that is what we talk about, ability of sensor to provide the same or alike results within some statistical distribution, right? And the accuracy would be the capacity to provide a mean value close to the true value, right? So again, 3 sigma or 2 sigma, whatever you decide for that measurement of a system. So that's precision and repeatability. We repeat it, how tight is the distribution? Is it still close to the signal that we measured before? Now, we are talking about sensors in general, but we are interested in nanobiosensors, right? And the simple reason is because miniaturization has given us many more benefits for many varied reasons. Don't get scared. I just wrote this some time ago, and I like to go through this. So the size of biosensor at micro and nanoscale has given us better signal to noise ratio, which means that it's the same idea like a radio station, the old radio set. So you have to tune it precisely to measure. Now, when you make it small, so we have an interface which is about the same size as the analyte that we are measuring. So we can tune into exact size and scale of what we are trying to measure, reducing or getting rid of noise. And noise here being other molecules or the ions that are floating around. So the surface to volume ratio of making them smaller has increased the sensitivity. Now, the active area is much more than the bulk of the sensor itself. So if you are using a bigger one, your surface to area ratio is smaller, you're making smaller one, so you can deploy many more and get much bigger signal from a given system. We can bind and use many naturally occurring and synthetic materials together because of our knowledge now from what we call bottom-up assembly, bottom-up synthesis. So that gives us another control or another capability of making new materials. We can control, direct, and manage molecules in a much better way. We can engineer how and where do they bind. This was the example we saw last time, right? So they designed and I call it a primitive example today. It's from 96. We have become much better in designing genomic things. So there's a genetic engineering big area of just designing different structures of DNA, which will result into actual physical assembly of things, nanoparticles, nanowires, whole bunch of things. So we can control and direct these things at small scale much more precisely. Now, that gives us the better sensing capability, and if you can sense it, we can cure it also. If we can measure it, we can do something to provide drug molecules to that as well. Better electronic circuits have given us much more sensitivity in measurement. Picoamps is straightforward now to measure. So think about, we are measuring very small current now, and that can be a transduction of a few molecules, down to few molecules or few hundreds of molecules, picomolar, nanomolar, femtomolar kind of measurement. And so that electronics has also become smaller and much more precise. It can get rid of noise in not just electronics, optical side also. Optical and electronic circuits have become much, much more where they can precisely find and measure the signal which happens because of self-assembly of molecule or binding of those molecules with things that come in contact with them. So electronics and fluorescence material, they come, so electric electronics and fluorescence is the optical side to it. So this gives us the capability of going down to single molecule detection. And so much so, single nucleotide change detection as well. So there's some work we have done where we could see one base mutation. And one base mutation is the ultimate mutation, right? So the mutations are always a bunch of bases that go back, which result into mutation. And then we know mutation results into cells that become diseased, right? X-Men. They are doing something else than they're supposed to do. And we can, with nano devices, we can go down to that kind of detection with these sensors. And in all those cases, we have to know these parameters, these properties or performance metrics for our sensor.